Hi, I'm Charles Kaplan, a professor at the State University of New York at Old Westbury, and this video is the second of about a dozen I'll be making on hypothesis testing. And thus far you've learned how to calculate the mean, which is a point estimate, how to measure the standard deviation, which is a measure of the variability of the data, and you've learned how to create confidence intervals, which provide an interval rather than a point estimate of the mean. So now you're learning how to determine if the estimate of the mean is what we call statistically significant. That is, when we sample the data, could we obtain the measure of the mean by luck or chance, or is it indeed representative of the true population mean? So, in order to do that, there's some steps that we're going to take, and I list them here. We want to list the important information, and that includes the population mean mu, the sample mean x bar, the sample size n, the sample standard deviation s, and the level of significance alpha. We then want to draw a picture. We want to find the critical values. We want to identify the null and alternate hypotheses, h sub 0 and h sub 1. We want to form a decision rule. Then we're going to calculate the test statistic, which is z or t, and then we're going to form a conclusion based on what the value of z or t is relative to the critical values that we determined earlier. And then we're going to, write up what our conclusions are. So let's get to a problem. Oops, this was the first problem I did. How about getting the second problem here? How about this one? A food manufacturer is worried that its 16-ounce cans of peaches are being overfilled. After taking a random sample of 50 cans, it was found that the mean weight was 16.05 ounces with a standard deviation of 0.03 ounces. At the 5% level, is the mean weight greater than 16 ounces? And we also want to know what the p-value is. Now, this is an important consideration on the part of manufacturers. In other words, if the 16-ounce can, and they advertise that it's 16 ounces, if they're underfilling the can, then they're harming the consumer. If they're overfilling the can, then they're harming their stockholders, because then they're wasting, it's too much money. They're giving away peaches then. So, okay, so let's work the problem here. So the first thing we're going to do is list the important information. Well, we know that mu, the population mean, is 16, and we know that x bar is 16.05. We know the sample size is 50. We know the standard deviation is 0.03, and the question asks us to work at the 5% level of significance. So now we're going to draw a picture and try to show visually what we're talking about here. We know that this is 16. Now, here comes, well, that's what we've got so far. Let me just leave it at that, and we want to determine the critical values. Well, okay, we need to go to the question. The question asks, at the 5% level of significance, is the mean weight greater than 16 ounces? Okay? Is it greater than 16 ounces? So we're working to the right tail. That's the question that students always have is this a one-tail test, a two-tail test? If it's a one-tail test, which tail are we working on? Well, there's the question. Is the mean weight greater than 16 ounces? And in this particular case, we're going to have 0.05 in the tail. Okay, now we're ready to determine the critical value associated with this. This is the z value associated with 0.05. And let's get our book out. Well, first, we know that there's 50% of all observations are to the right of the mean, 50% are to the left of the mean. And so 0.05 less 0.05, 0.5 minus 0.05 is 0.45. That's this region right here. So in our textbook, at the back of the book is the z table, and the 0.45 is the area. You see that we're working with the central area here. So we're going to look for 0.45, and 0.45 is right here between 1.64 and 1.65, 0.4495, 0.4505. So 0.5 is right in the middle. So we're going to take 1.6, we go down to 1.6 and over to here, and right in the middle would be 1.64 and then plus a half, 1.645. So that's our Z value, and let's put that in here, 1.645. I don't know what the X value is associated with this, but maybe we'll have a little time at the end to calculate that, the cutoff point. But for now, 1.645, that's our Z value. That's the critical value. Now we're ready to compute the null and alternate hypotheses. H sub 0 is the null and H sub 1 is the alternate, and I always start with the alternate first. And the alternate is the hypothesis that answers the question. In this case, is the mean weight greater than 16 ounces? Well, that's going to be our alternate. Mu greater than 16. And the null, then, we just reverse this. Mu less than or equal to 16. Remember, we need to put the equal sign in here. Okay, so we've listed the important information. We've drawn a picture, determined the critical values, and written out the null and alternate hypotheses. Now we're going to form a decision rule. That decision rule tells us under what conditions we're going to reject the null hypotheses. Well, we're going to reject the null hypotheses if our test statistic, Z or T, falls to the right of negative 1.645. So we're going to reject the null hypothesis H naught if Z is greater than 1.645. There's our decision rule. Reject the null hypotheses if Z is greater than 1.645, which is the critical value associated with this point here with 0.05 in the tail. Okay, so now we need to calculate Z. And Z is equal to x bar minus mu over sigma, or in this case S, over the square root of n. So we've got 16.05 minus 16 over the standard deviation, which is 0.03, over the square root of 50, which is n. And if you do that, I believe it works out to be about 11.79. Now, 11.79 is way to the right of 1.645. In fact, the likelihood of obtaining a Z value of 11.79 is virtually zero. I mean, it's indistinguishable from zero. So there is no question in this case that the production line needs to be shut down and the machinery is overfilling these cans of peaches. So our conclusion, and what we're going to write up in our conclusion, is that the mean weight is greater than 16 ounces. Right? Significantly greater. I mean, there's no doubt about it here. 11.79. We're talking these are units of standard deviation, by the way. Z values are units of standard deviation. So 11.79 standard deviations from the mean is so far out, it's almost impossible to get it by chance. So definitely overfilling here. Now, what's the X value associated with 1.645? Well, we can determine that. So we've got 1.64. Remember, our equation for z is equal to x bar minus mu over s over the square root of n, the standard deviation of the square root of n. Okay, so if we fill in our numbers, we already calculated z. We're interested in the x value associated with z of 1.645, the cutoff point. So 1.645 is equal to, well, we need to find that value of x minus mu. Mu is 16, sorry about that, over 0.03 of the square root of 50. Now, how do we handle this compound fraction? We invert and multiply, so we're going to have 1.645 is equal to x minus 16 times the square root of 50 over 0.03. So if we multiply 1.645 times 0.03, we get 0.04935 is equal to x minus 16 times the square root of 50. And if we divide by the square root of 50, we get 0.006979 is equal to x minus 16. So x is equal to approximately 16.01. So if we go back over to here to our little picture, this is 16.01. So there's a 5%, 5% of all observations of these cans are going to be greater than 16.01. That's what I just determined. Okay, so that's hypothesis. Let's calculate the p-value. Well, the p-value is not going to be distinguishable from 0. P is equal to 0. 11.79. There's nothing to really look up or do. So, okay, my name is Charles Kaplan, and this was the second video on hypothesis testing. If you found it helpful, I really would appreciate it if you leave some nice, favorable comments for me. And I wish you all good health, good happiness, long lives, and a lot of luck. Bye-bye.